All right, so in this chapter, we'll learn to describe one-dimensional motion. Okay, what does that mean?
Just on one axis?
That's right. So we will be looking at an object that moves in a straight line. Okay, it can move back and forth and so on. All right, so for instance, we will be interested in describing where the object is at any given time. So the location of an object is given with reference to a coordinate system. Okay, so what this is telling you, showing you is that's the origin of the coordinate system. And you see distances to the right are marked as positive, and distances to the left are marked negative. Okay? That's just a convention. You can mark positive that way or mark positive this way, it doesn't matter. Okay? All right, so we will choose a coordinate system and we will give your position with reference to that. Okay. Now, what is speed? Is speed a vector or a scalar? A scalar. What is velocity? It's a vector. Okay. Now notice something. In one dimension, a vector can only point either to the left or to the right. Okay. So let me backtrack a second. To represent a vector in 3 dimensions, how many numbers do you need? 3. Why do you need 3 numbers? 2 for direction and 1 for magnitude. Okay. In one dimension, the vector can either point to the right or to the left. Okay. So the sign, so plus 5 meters per second, you don't need a number for direction. It's the sign that tells you the direction. Okay. So that's the convention. So plus 5 meters per second is a velocity pointing to the right, and minus 4 meters per second is a velocity pointing to the left. Okay. So in one dimension, this is a special case. You don't need a number to specify the direction. It's the sign that tells you the direction of the vector. Okay. So keep that in mind. All right, now before I get into this, so here's what we are interested in, really. So yeah. So let's say here's an XYZ coordinate system. You get on in your helicopter or plane or whatever and go on a flight. Okay. This is what we are interested in describing. We are interested in describing this 3-dimensional motion. All right, what does describing the motion mean to you guys? What would it mean to you? Yep. I'm sorry? Yep. You're describing where it's going. So how would you do that? I'm sorry? Okay, so yep. So if you think about it for a while, the most succinct way to describe it would be, this would be your position vector. What is your position vector? The position vector is a vector pointing from the origin to where you're located. Okay? And this is where you were located at this time. Okay? So the best way to describe your motion is giving your position as a function of time. And that's what we mean by describing the motion of an object. Okay? So if you give your position as a function of time, if you give this, then I can calculate everything that I want to calculate about your motion. I can calculate the velocity, your acceleration at any time. Okay? So this is what I'm interested in. Okay? All right, so here's a general 3-dimensional motion. Now it turns out that, so if you're here, you can take a projection of this point along the x-axis, projection of that point along the y-axis, projection of that point along the z-axis. Okay, or I will say, so RT is XT I plus YT j plus zt k. Do you guys understand this? What this is telling you is this is where you were located at this time. This is your x coordinate at that time. There's your y coordinate at that time. There's your z coordinate at that time. Everybody understand them? Okay. Now it turns out that, okay, so for three mutually perpendicular direction, this motion is independent of that. That is, if you apply a force in the x direction, you do not change y or z motions. Okay? So each motion is independent. Okay? So what we'll do is we'll simplify things, and in this chapter we'll only consider one-dimensional motion. Okay? So you will learn how to describe one-dimensional motion, and once you learn how to describe one-dimensional motion, then you can put as many dimensions as you want. Okay? And that's the idea. Okay? Yeah.
Could you label the equation again like we did before? R is where we are. That's the origin.
This is the origin.
And then R,
This is where you are at time t.
and then the equation. Like how you explain it? Can you say that again?
Okay, so R is your position vector, and the position vector is a vector from the origin to where you're located.
And then X, T.
Okay, so let me draw another cleaner diagram. Okay. Okay, so let's say you are here. This is R. There's the projection of R on the xy plane. And this is x. So this, if this were xt, rt, this would be xt. And this would be yt. Did you understand that? Okay. All right, so what are we interested in? Describing 3D motion, okay? And what does describing motion mean?
Describing the position.
Giving the position as a function of time, okay? So if you have this guy, if you have your position as a function of time, you have a complete description of the motion. Okay. So let me start off with an example. Okay. Okay, let's say, and we'll do a one-dimensional motion. Okay. So for instance, let's say you're driving on a straight road, okay, and Daytona Beach is the origin, and you're driving on I-95, let's say, okay, and your location is given by 5t³ plus 7t squared plus 8t plus 10. Okay, and this distance is measured, well, we'll keep it simple. The distance is measured in meters. Okay, now notice something. Okay, so this is in meters. Okay, each term has to be in meters, right? Okay, what are the units of this guy? Meters. What are the units of 8?
Meters.
Meters per second. Time is measured in second. Okay, so that'll cancel. So this has to be in meters per second. What are the units of 7? Meters per second squared. So that's related to acceleration. What are the units for this guy? Meters per second cubed. Okay, you guys understand that? All right, so we will see in this chapter. So here's your position. And I said, once you have your position as a function of time, you can calculate everything that there is to calculate about the motion. Okay? A couple of the things that you will be interested in is velocity and acceleration. Okay? And the velocity you will see is given by the time derivative of the position. Okay? So the velocity, what does this tell you? What is the velocity of the object at that time? So this will give you the velocity as a function of time, and that is given by 15t squared plus 14t plus 8. Okay? So given this position as a function of time, you were able to calculate the velocity at any given time. Okay? And you will learn acceleration at any given instant is time derivative of velocity as a function of time. Okay. How many of you have not seen derivatives in class yet, in your calculus class yet? Okay. You haven't seen. Do you know what it means?
You said derivatives?
Yeah.
Oh, no, yeah.
You don't know what it means?
No.
All right, we'll talk about it in a second. All right, so you will see acceleration is derivative of velocity as a function of time, and the derivative of this is 2t, that's 30t. Derivative of t is 1, so 14, and so on, okay? We will come to derivatives in a second, so let me repeat what we said. Okay, so what we are learning to do in this chapter is to see how to describe motion. Okay, and to describe motion, what you want is the position as a function of time. Okay, so whenever somebody gives you this position as a function of time, what they've done is they've described a motion to you. Okay? So they've given you a complete description of the motion, and from that you got the velocity at any given time, and you got the acceleration at any given time. Okay? And that's what you're interested in. All right, so now let's step back and do a little review on derivatives and integrals. Okay? So how many of you are in Calc 1 right now? So none of you guys have done derivatives yet. Have you done derivatives yet? Okay. All right, before we go on to that, do you have any question on what this chapter is about? All right. So let's do derivatives and integrals. Yeah. And by the way, so you can also go to my YouTube channel and review this afterwards, but we'll study this right now. Okay, these are two things that you'll be interested in this class. Okay, so we will be using this. This will be like a tool that we'll use. Okay, you guys all know what a function is. Okay, so here's a function. Okay. Now there's a couple of things we are interested in. Okay, so let's say at this value of x, okay, here for this value of x, that's the value of the function. Okay, so one of the things we are interested in is how fast is the function changing at that point. At this point, how fast is the function changing? If you go to the right, what is happening to the function? What is happening? I'm sorry? It's increasing. And one of the questions is how fast is it increasing? Okay, so here it's increasing. At this point, it's decreasing. At this point, it's increasing faster than at this point. Okay, so you are interested in the rate of change of the function. Okay. Can you think of a good way to measure it? Go ahead. Very good. Okay. So what our friend just said is to figure out to measure the rate of change. What you go is go to that point, draw a tangent line to the function, and the slope of the tangent line tells you the rate of change of the function. Okay? And the slope of the tangent line you will learn is df by dx is equal to the derivative. Okay? So the derivative of a function gives you the slope of the tangent line at that point. Okay? Like our friend said. Okay? So now let's learn how to do derivatives. Okay? And we'll give you a laundry list of derivatives. Okay? And you will see the derivation of this in your calculus classes. Okay, so you understand what the derivative does? It tells you the rate of change of the function, and it's equal to the slope of the tangent line. Okay, in this one-dimensional case. All right, so you will learn to do this. So if the function is x to the power n, the derivative of the function is n x to the power n minus 1. Okay, if the function is sine of x, the derivative of the function is cosine x. Okay. So what does this mean? So let's draw sine x, okay? Okay. So if you draw sine x, the derivative was the tangent to this slope of the tangent. So if you took the derivative there, that would be equal to cosine x is what we're saying. For this value of x, the slope would be equal to the cosine of x at that point. So that's what it's saying. Okay. You guys understanding this? All right. If f of x is ex, df by dx, anybody know what that is? E to the x. That's the only function whose derivative is itself. Okay? F of x is log of x, df by dx is 1 over x. All right, so again, you can look up tables. It'll give you derivatives of functions and so on. Okay? So in our example, all we used was this one. If you had x to the power n, the derivative of that was n x to the power n minus 1. Okay? So if your function was t cubed, what was the derivative of? I'm sorry? 3t squared. Okay? So that's what we used there. Okay? So your position as a function of time was 5t cubed. When you take the derivative of that, you get 3t squared. 3 times 5 is 15t squared. Okay? Then you take the derivative of the second term. What is the derivative of t squared? 2t. 2 times 7 is 14t. What is the derivative of t? 1. Okay? So that's 8. Yeah. Again, you take the derivative of this. Derivative of t squared is 2t. 2 times 15 is 30. 30t. Okay? Derivative of t is 1. So there's the 14. All right. What does the derivative give you? Slope of the tangent line. Very good. Okay. And if your function happens to be the position as a function of time, the derivative of that equals the velocity at that time. If your function happens to be the velocity as a function of time, the derivative of that happens to be the acceleration. Okay. So that's why we're interested in that. Okay. Any questions before we move on? Because once I get to the slides, I'll move fairly quickly. Okay, do you guys understand this? Yeah. Anybody else back there? Okay, here's another thing. I want you to sit so I can see you directly, okay, because I'll be asking everybody questions. I don't want anybody hiding behind people. So you'll have to move. Okay? You'll have to move as well. No, not you. Yep.
So I guess
Mhm.
question.
Mhm.
Since there's no exponent for the 10, since it's, there's no t next to
Derivative of a constant is 0.
it. Okay.
All right. So one of the things we wanted to learn was how a function changes. Okay. The other useful thing for us is the following. Okay, so here's a function. Okay. What we want to know is what is the area under this curve from x1 to x2. Okay. And this area is given by this guy, the integral. Okay. So we are interested in that. Okay. And now, integrals, they also are called antiderivatives. Okay? So what that means is the integral of a function is, okay, so let's, so if the, so here's the fundamental theorem of calculus. This is fx x2 minus x1. All right, what is this fella? What's that? That's the integral. What that means is the derivative of fx, capital Fx, is equal to fx. Okay? So this function is, if you took the derivative of that, you would get that function. Okay? So that's what the integral, that's the antiderivative. And then you evaluate this at these 2 points. Okay? So this is equal to fx2 minus fx. Okay? And what is this number equal to? That's equal to this area. Okay. That's equal to this area from x1 to x2. Okay. So the area under the curve is given by the integral. Okay. All right, let's see if everybody understand that? Okay. So what are the 2 things we are interested about for functions? How, at what rate they change, and what is the area under the curves? Okay. And of course, we will generalize this to higher dimensions and stuff like that. Well, so we'll generalize the concepts. Okay. All right, so can you tell me what is the integral of x to the power n? X to the power n plus 1 divided by n plus 1. Okay, how do we know that's true? Well, let's take the derivative of this and make sure we get that. Okay, so let's verify that. D by dx of x to the power n plus 1 over n plus 1. We want the derivative of this to equal that, right? Okay, so 1 over n plus 1 is a constant, so that 1 over n plus 1, that's a constant. D by dx of x to the power n plus 1. Okay, and we know the rule. The derivative of that is n plus 1 times x to the power n. And this cancels that, and that's equal to x to the power n. Okay? All right. So what we are using is this rule. The derivative of x to the power n is n to the power x to the power n minus 1. Okay, that's the rule we used. Do you understand now? Okay. So essentially, all right, so you can look up a table. If you have x to the power n, it's n x to the power n minus 1. Sine x is cosine x, derivative of that. Cosine x is minus sine x, and so on. Log x is 1 over x, okay? And e to the power x is e to the power x. So going this direction, you're getting derivatives, And if you take the integral of d, okay, so integrals undoes the derivative. That's why it's called the antiderivative. If you take these functions, the integral of this function is that. The integral of this function is that. The integral of this is that. No, you live in the age of Google. Google anything. You know. What I want you to do is understand what it means. Okay? All right, my friend. What does an integral tell you? I'm sorry? There you go. Very good. All right. Do we have any questions? Yep.
So in physics, what does the integral like signify? You said that
So you will see that
it.
you will see in different situations it will mean different things. Okay. If this happens to be velocity as a function of time, then that would be the displacement. If this happens to be the force as a function of position, this will be work. If this happens to be acceleration as a function of time, this will be the change in velocity. Okay, so it depends on what it is, the function. Okay, so it will signify different things, and we'll see all of that. Okay. How you doing, my friend? You understand? Okay. All right. You paid for it. If you have any questions, you might as well ask. All right. All right. Any questions before we go into the slides? All right. So we are interested in 1D motion. That's one-dimensional motion. So we will be looking at objects that move only in a straight line. Again, the line cannot be curved. Okay. So we'll be looking at an object that moves in a straight line. Here's another thing that we didn't mention. Okay, so we will be looking at this car moving like that. Now, what we didn't say is we'll treat these objects as a point object. Okay, what does that mean? We can treat this motion, we can treat this object as a point object only when every point on the object is moving with the same velocity. What that means is the car is not spinning. So we are describing the simplest kind of motion. Okay. If the car were spinning and going back and forth, then every point on the car is going with different velocities. So you have a million points with a million different motions going on. Okay. So we don't want to get into all of that. For now, we'll be describing the motion of objects where every point on the object is going with the same velocity and same acceleration, obviously, and so on. Okay. So we will be treating objects as point objects. Okay, so what does this tell you? So what is this picture? So this is giving you the position of the object as a function of time, okay, with reference to this coordinate system. Okay. I don't want to confuse you, but we are referring everything with reference to this coordinate system. There's nothing magical about this coordinate system. I can choose another coordinate system. I could choose a coordinate system where that is the origin and that is the positive direction, 10, 20, 30. This is 0, 10, 20, 30, and this is minus 10. Okay. With reference to this coordinate system, the same motion would be the same graph that's reflected on the x-axis. Did you guys understand that? Okay.
No. So why is 10 negative and all other numbers?
Okay, so if with reference to this coordinate system, at t equal to 0, it's at minus 30. It would be at minus 30.
So which one are we describing, the first or the second?
Oh, we are describing with reference to this coordinate system. This graph is with reference to this coordinate system. The same motion can be described using other coordinate systems. Okay, the graph would look different. Okay? Maybe I shouldn't have said that. But anyway, you guys understand? So what is this graph telling you? This graph is telling you at t equal to 0, the object is at 30 meters. At 10 seconds, it's at 50 meters. At 20 seconds, it's at that point. Okay. So you see, it's giving you the location at all instants. It's giving you the location of the object at all instants. So this is a complete description of the motion. Okay, this is equivalent to giving you x equal to t. This is just a plot of x equal to t. Okay, yep. Mhm.
So, the graph, the one-dimensional
Mhm.
coordinate system has a two-dimensional graph in relation to time, and
Right.
so on and so forth.
Right, right. So if I showed you a movie of this thing, the timestamp would be in the different frames. If I showed you a movie, you can't calculate the velocity and so on, okay? So you have to translate that movie into this graph.
Yeah.
Or you have to translate that movie into this function as a position as a function of time. This is what's most useful for calculations. Okay? If somebody throws a movie at you, you're up the creek. Okay? What you want is position as a function of time. And then you can calculate stuff. Okay? Do you guys understand? Okay. So next time I ask you if to describe a motion, what is it that I'm asking you?
Position as a function of time.
Give me the position of an object as a function of time. Okay? I don't want a verbal description of stuff. I want a mathematical description of the motion. Okay? So we consider motion of particles or objects that move like a particle. Every part of the object has identical motion. Okay? Vectors and scalars, you saw that the quantities that we will be dealing with in describing motion either can be described using vectors or scalars. Okay, so velocity, acceleration, displacement, these are all vector quantities. Speed will be a scalar quantity. Okay, speed is how fast you're going. Velocity is how fast you're going, plus which direction are you going. Okay. You guys understanding this? Okay. Okay, so what is this? This is position as a function of time. Okay, so here is the motion of this guy this is the physical motion, but again, like I said, if I showed you a movie of this, that will not be useful to do calculations. What is useful is this graph. Why is this graph useful? It's telling you where it is at all times. This is essentially giving you x as a function of time. And then you saw that given that, you can calculate all kinds of things that you're interested in. Okay? All right. So the position is the location of the particle with respect to a coordinate system. A position versus time graph is a graphical representation of the motion. Okay? That's a graphical representation of this position as a function of time. Okay? All right, so now we'll we'll define the first physical quantity. We'll describe displacement. Okay, so in this graph, again, here's time flowing in this direction. What this means is, okay, so here you start at home, you go for a walk, and again, we're doing one-dimensional walks, one-dimensional motion, so you're going to walk in a straight line. So you walk to the right half a kilometer, and then as time proceeds, you walk back. Okay? Your displacement, which is a vector, Okay, so here we are not using arrows. Your displacement is your final position vector minus your initial position vector. Okay. And in this case, and this vector, displacement vector, just points from the initial point to the final point. So if this is your initial point, and there's your final, okay, there's your final point, your displacement vector is this vector. This is delta x. Okay. Let's say you, in one dimension, if you went there and came back, what is your displacement vector? 0. Okay. For this motion, what is the displacement vector? This is your displacement vector. Okay, that's delta x. All right. So again, this is better seen in 2 and 3 dimensions. Okay, so let's say in 3 dimensions, let's say you go like that. This is your initial point, and there's your final point. The displacement vector is that guy. That's your displacement vector. Okay? The displacement vector is a vector pointing from from your initial point to your final point. Okay. Distance, on the other hand, distance traveled is a scalar. Okay? So for this guy, for this motion, what was the displacement? 0. 0 vector. Okay? So that was the 0 vector. What was the distance traveled? 1 kilometer. For this motion, the displacement was 0.75 kilometers pointing to the left. So delta x, your displacement is minus 0.75 kilometers. Remember the negative sign telling you that the vector is pointing to the left. Okay? Kilometer. That was your displacement. What is the distance for that displacement for this motion? 1.75 kilometers. Okay? Okay, 2.75 kilometers. Okay? So the distance traveled was that. Okay? All right, so again, displacement is a vector quantity. This is a scalar quantity. Yeah. Okay. So going back to our 3-dimensional example, this would be the displacement. The distance traveled would be that distance. Okay. All right. Again, don't get overwhelmed. Don't get confused. You'll be amazed. You'll understand all of this as we go on. Okay. And the thing in education is the following: if you think something is hard now, the way we make this easier is to teach you something harder. Then this becomes easier. All right, so that's the idea. We keep throwing you in deeper and deeper ends. Yeah? And that's the idea. All right. The next quantity we'll define is average velocity. What do you think this is? A vector or a scalar? I'm sorry? Yeah, this velocity is a vector. An average of a vector quantity is a vector. Okay, so average velocity is, you see, this is a vector, displacement divided by time. Change in time is a scalar. This is a vector. So vector divided by a scalar is a vector. Okay, so here's how you define average velocity. Displacement divided by time. All right, let's say you go to Palm Coast and come back. What is your average velocity? 0. Okay? Because your displacement would be 0, and whatever time you took, 0 vector divided by a quantity, finite quantity is a 0 vector. You go to New York and come back. What's your average velocity? 0. You go to Paris and come back. 0. See, the average, it's not a very descriptive quantity, is it? No. Okay, it doesn't tell you details about anything. I can say that the average height here is 5.66 inches or whatever, let's say. And then what I can do is I can bring a whole bunch of NBA players and a whole bunch of midgets and still keep the average the same. Right? All right, so average quantities are not very descriptive, but sometimes they can be useful. Okay, now let's look at the units. Displacement. This is measured in meters, that's in seconds. So velocity, units for velocity, SI units for velocity are meters per second. Okay. Average speed, speed is a scalar, so average speed will be a scalar. Okay. Speed is defined as distance traveled divided by the time over which you did that travel. Okay, so you go to Palm Coast and come back, your average velocity was 0. Your average speed is, I'm sorry? Something. It's not 0. Okay? All right. It'll be smaller the longer time you take to cover the same distance. Okay? And you take less time to cover the same distance, the average speed will be higher. Okay? So average speed and average velocity are not related. Okay? But it turns out we will talk about instantaneous velocity and instantaneous speed, and they'll be related. Okay? So these two guys are not related. Mm-hmm.
Would there be a situation where average velocity is not 0?
Sure. For this guy, average velocity is not 0. If your final point is the same as your initial point, then the average velocity is 0. For just this journey, average velocity is not 0. For just this journey, average velocity is not 0.
So if displacement is 0, velocity is 0?
Very good. Okay. If that was the key. All right. Now you guys are all experts at calculus, so average velocity is for kids. You want instantaneous velocity. Yes, you want it. You want to know how fast am I going and in what direction at this instant. And I want to know that at every instant. Okay? And so instantaneous velocity is, what is this guy? This is the average velocity. Average velocity in the limit delta t going to 0. And in your calculus classes, you will learn that this limit is the derivative of that function, is the derivative. Okay? So the instantaneous velocity is given by the time derivative of the position of the object. Okay? So this is the one-dimensional case, and we will generalize this to the three-dimensional case in the next chapter. Okay, so this guy was dxt by dt. This was the instantaneous velocity in the one-dimensional case. Okay, and that can easily be generalized to the three-dimensional case. And I'm going to do that right now because you guys are all experts. Okay, so let's do this. Okay. So what does describing motion mean? We want to give you the position as a function of time, right? This is equal to x of t I plus y of t j plus z of t k. Okay, what does this mean? This is the x coordinate as a function of time. This is the y coordinate of your plane. This is the z coordinate. Okay? Let's make up some functions. So I'm going to do 5t squared plus 6t plus 7. You guys understanding this?
You're doing instantaneous velocity?
Yeah, we're going to do instantaneous velocity. And I'm going to do it in 3 dimensions. Okay. Okay, so this will help you out with taking derivatives as well. Yes, it'll help you out.
What is that second part of the last function, the plus six?
The cosine?
The cotangent?
This is 7t³ plus 8. This is e to the power of 3t plus cosine t. All right. So what does this tell you? What does this give you? Where you're located at this time. So this is giving you your location as a function of time. Everybody understanding this? I'm already introducing the next chapter. All right. So if I want to know my velocity at this instant, what do I do? I'm sorry? Yeah, you take the time derivative. So velocity at this time is the time derivative of this function. Okay, so it's taking the time derivative of this guy. So you take the time derivative of this function. That'll give you an x component of the velocity. You take the time derivative of this function, and then you take the time derivative. All right, who wants to help me out with the first guy? So this is the x component of your velocity. Okay? Plus, all right, my friend, hello there. You, give me the y component of the velocity.
21t squared.
21t squared. Okay. Hello there. Hello? That's okay. So what you do is you'll have to use the chain rule, which I guess you haven't studied yet. So if this were just t, it would be et, but this is 3 e to the power of t minus sine t. Okay. Did everybody understand that? Yep.
So the first equation you gave us was the position equation, and then you took the derivative, so you got the velocity equation.
Right.
And then you just plug in for t.
Yeah, so if you wanted to find velocity at 3 seconds, you would put 3 seconds for t.
Yeah.
What would you do if you wanted to find the velocity at 5
I was
seconds?
just a little confused because you didn't state that you wrote down the position equation.
Right,
before.
right. Okay. Okay. All right, everybody understand that? Yep. Okay, so derivative of e to,
E of x equals e of x. How you still just do
well, I'm sorry? Yeah, it's a chain.
Can you go back so we finish?
Yeah. Any questions on that?
If it's a chain rule, then wouldn't, you see how the power is 3t, wouldn't that be a 2t?
No, okay, so the chain rule is like this. I'm not going to, so, okay. D by dx, f of gx is f prime g prime x. Okay, what that means is, let's say, okay, so so think of this as x.
You start with the exterior first.
Yeah. Okay, so if this entire thing were x, what would be the derivative of that? 4 times this cube,
Yeah.
okay? So derivative of that would be 4 times x cubed plus 7 cubed. But this is not x, this is g of x. Now take the derivative of that. Times 3x squared plus 7. So that's how you would take the, okay? So applying the same thing to e to the power of 3x, okay, so if this were x, the derivative of that would be e to the power of 3x, except that that's not x. Now take the derivative of that, and that would be 3.
Well, would the exterior for that be the power rule?
Okay,
Or would your initial step be the e?
yeah, let me, so, all right, so this is, I don't know how to say. Okay, this is, think of this as y.
Yep.
So derivative with respect to y would be, okay. So let me use another notation. So, so think of this as y, and you're trying to take the derivative with respect to x. So this would be dy times dy by dx. Okay, so d by dy, so we are doing a change of variables times dy by dx. Okay, this derivative is ey, and dy by dx is 3. Did you understand that?
Yeah.
Okay. So that's the chain rule. We use the chain rule. All right, so I need to go back to the previous slide. Okay, again, I'm throwing a lot at you guys. I'm throwing 2 chapters at you, okay, at the same time, because why am I doing that? Because you guys are experts. Okay. So here's a position as a function of time. There's the x coordinate as a function of time, y coordinate, z coordinate. There's the x coordinate. There's y coordinate as a function of time, z coordinate as a function of time. You wanted the velocity at a given instant, you just take the time derivative of position. There's the velocity. Okay, now what is the next thing you're interested in? Acceleration as a function of time. What is acceleration? Time derivative of the velocity. All right, my friend, you help me out. What is the acceleration?
I don't know the size of what's going on.
I'm sorry?
I don't know the size of what's going on.
I'm sorry?
I don't know what's going on.
Oh, you don't know what's going on. Okay. How come you're not asking questions?
There are no number of questions that make me understand this.
I'm sorry?
There are no number of questions that make me understand this.
All right. Well, you weren't paying attention either then. If you don't know something, it would behoove you to pay attention. All right. Hello there. You help me out? Yeah. I'm sorry? Yep. So what is the derivative of this? Very good. 10. Next. 42t plus, if you take the derivative of this again, you get 3 e to the power of 3t, so 3 times 3 is 9, 9 e to the power of 3t, derivative of sine is cosine. Okay. So again, don't worry about it even if you didn't understand this. So what we are telling you is, here's the position as a function of time. Here's a 3-dimensional motion. What you are interested in is calculating these 2 quantities, velocity and acceleration. Okay? All right. Okay, so you learned that the derivative is really slope of a tangent line. So if you wanted to calculate the velocity at this point, the instantaneous velocity would be the slope of that tangent line. Okay? And what this diagram is showing you is the limit displacement over time. So if the time difference was that would be the slope of that line. And as you make this time interval smaller and smaller, you come to the limit of the slope of this line tends to the slope of that tangent line. That's what this is telling you. Okay? All right, so velocity, instantaneous velocity, is the slope of the tangent line drawn at that point. Okay? So if you wanted to find the velocity, instantaneous velocity at this point, you would draw the slope of that, you would draw a tangent there, and the slope of the tangent would be equal to that. Okay? Yeah. Instantaneous speed is magnitude of the instantaneous velocity. Okay, so what this means is the following. Let's say you're driving north on 95 at 80 miles an hour. What is your instantaneous speed? 80 miles an hour. What's your direction? North. Okay? So instantaneous speed is what your speedometer is reading at that instant. Okay? Acceleration is defined as follows. Change in velocity divided by change in time, over the time over which that change happened. Okay, so if you're accelerating, your velocity needs to change. If your velocity is not changing, your acceleration is zero. Okay? All right. Is this a vector or a scalar? That is a vector. A vector divided by a scalar is a vector. Okay? What are the units? Okay, units of velocity are meters per second divided by second, which is meters per second squared. Okay? So those are the units for acceleration. All right, now so this is average velocity, okay? And so what you're interested in is instantaneous velocity, instantaneous acceleration. Again, here's the average velocity in the limit delta t going to zero. That's the instantaneous acceleration, and this is equal to dv by dt. Okay. All right. So and the derivative of velocity with respect to time is also equal to the second derivative of position with respect to time. Okay. All right, so this chapter is about describing motion. Okay, describing motion of an object. And what we have learned so far is, in one dimension, describing motion means giving this, and giving this. Once you have that, if you wanted to calculate the velocity at any given time, that's how you calculate the velocity at any given time. And then if you wanted to calculate the acceleration, that would be the acceleration at any given time. So that's what we've learned so far. We spent a whole hour and all we learned is 3 things. Okay? We learned how to describe motion. From that we calculated the velocity. Okay? From the velocity we calculated the acceleration. Well, why did we calculate this acceleration? 2 chapters from now, you will learn if you want to give that acceleration, this is the force you need to apply. If you want this acceleration, this is the force you need to apply. Okay? And given this acceleration, then you will get that motion. So for instance, Elon wants to send a rocket from here to there. This is what he wants. Okay? He wants to go from here to there, and so he has to apply this kind of force to get from here to there. Okay, so that'll be our interest. Yep. Mm-hmm.
So instead of acceleration, it's just a double derivative of the position.
That's right. So that's what this is saying. Very good. That's very good. Okay. All right, you guys understand? That's the story. You have a question? Any question? All right. You all understand this? You look like you want to ask something.
No, I'm good.
Go ahead, it's okay.
No, I didn't actually have anything else, just zoning out.
All right. All right, so now we'll give meaning to area under curves. Okay, and I'll just show a couple of examples. Okay, so you already learned that instantaneous velocity is time derivative of position. Here's an equation. Okay, now in mathematics, if you have an equation, if you hit this guy with a hammer, you got to hit this guy with a hammer as well. All right. So what we'll do is, here's an equation, we'll take and integrate both sides of the equation. Okay, let's integrate this, okay, and what we'll do is we'll integrate this between T naught and T, and so you have to do the same thing to that guy. Okay. Now, you will learn from the fundamental theorem of calculus. Anyway, again, this is an integral of a derivative, so this is an antiderivative, so it just undoes that. The integral of this guy is just x of t prime, and then you evaluate it at the endpoints. Okay, it's x of t prime evaluated at that point, and that's what this is, x of t minus x of t naught. What is this guy? That's the, and this is called the displacement. Okay, this is your position at final time, and this is your position at initial time, and that's your displacement. And this displacement is that guy, and what is this guy? That's the area under that curve. Okay. So in one-dimensional motion, if you're plotting velocity as a function of time, the area under that curve gives you the displacement. Okay. If you plot acceleration versus time, the area under that curve will be your change in velocity. Okay, that's what that works out to. Okay. We won't worry about this too much. I just wanted to show you that. Okay, it won't be. We won't use this too much, but anyway, you know. Yep.
So like on the unit test and stuff, like, will you have the equations there for us?
Yeah, I'll give you a sheet of equations. Yep. So again, we are showing you this. This has the derivation of that. Again, dv by dt is a. Here's the equation. We're going to hit this with a hammer. So we are going to integrate that, integrate both sides. Integral of that is Vx. The integral of that is just Vx, and then evaluate it at these 2 points. There's that. So this is the change in velocity over that time interval. Okay? Change in velocity is the area under the acceleration curve. Okay? That's what that is. Okay, so here, this is something I want you to understand. This is a very simple diagram. Okay. Okay, what if the acceleration is non-zero? What does that mean? If your acceleration is not zero, what does that mean? When do you have non-zero acceleration? When your velocity is changing. Okay, so if you're accelerating, that means your velocity is changing. Okay. So what does this diagram show you? See, this, the red vector is the velocity vector. Is the velocity vector changing? No. So your acceleration is zero. Okay. Let's see here. In this case, the velocity vector, what is happening to the velocity vector?
It's growing because there's a constant acceleration.
Okay. let's be a little more technically sophisticated. The magnitude of the velocity is increasing. Okay? To change the velocity, how can you change the velocity? You can change the magnitude or the direction. Or you can change both. Okay? In this case, the magnitude of the velocity was increasing. Okay? And you see the magnitude increases if the acceleration vector is pointing in the same direction as the velocity. Okay? In this case, the velocity magnitude was decreasing because the acceleration was pointing in the opposite direction. Okay? So when you're slowing down, what does that mean? Your acceleration vector is pointing in the opposite direction as your velocity vector. And if you're speeding up, that means the acceleration vector is pointing in the same direction as the velocity vector. Okay? All right. All right, so what this graph shows you is velocity as a function of time. What is acceleration? Acceleration is dv by dt. So that's the slope of the tangent line. The slope is constant. So the acceleration corresponding to this motion is that. It's a constant acceleration motion. Okay? So this graph corresponds to that. Okay. Here, velocity is increasing, so the slope of the tangent line is increasing. Okay, acceleration is increasing, so this corresponds to that. Okay. How about for this guy? Here, acceleration is constant, the slope is constant, acceleration is constant, and non-zero. Here, acceleration is 0. Okay, so this corresponds to that. Okay. What does this graph show you? Here, acceleration is constant. Okay, so as time, acceleration is not changing. And this is the kind of motion that we'll mostly consider. We'll consider constant accelerated motion. And here's the only example that you see. Constant acceleration is very hard to maintain. You get in your car and try and maintain constant acceleration. You can do it for 2 or 3 seconds at best. Okay? You drop this guy has constant acceleration, and in a couple of seconds it hits the ground. Okay? So constant accelerated motion is very hard to come by. Okay? But that's all we're going to do, mostly. So when acceleration is constant, velocity increases linearly, and position is a quadratic function of time. So let me show that to you. Xt is 5t squared plus 6t plus 7. Okay, so what have I done? I have described a motion for you. Okay, here position is a quadratic function of time. What is velocity? dx by dt. Quickly, my friend, help me out. Help me out. Help me out. What's velocity? 10t plus 6. Okay, so you see, if position is a polynomial, velocity is a polynomial of degree 1 less. Okay, acceleration will be a polynomial of degree 2 less. Okay. So velocity will be a polynomial of degree 1 less, acceleration will be a polynomial of degree 2 less. So if this was t to the power 4, that would be t to the power 3, that would be t squared. Okay? And you see acceleration is twice that constant. Okay? So that's the acceleration. Okay? So whenever this is a quadratic function, which is a parabola, velocity will be a linear function and acceleration will be constant. Okay? And this is what we'll consider. So again, here's an example of a constant accelerated motion. Okay, so if you measure its position as a function of time, that would be a quadratic function of time. Velocity will be linearly increasing with time, and acceleration will be constant. Okay. So we'll keep things simple. we'll look at objects moving in a straight line with constant acceleration, okay? And so here is xt equal to x naught. X naught just means, okay, so x naught just means where you were located at time t equal to 0. V naught means your velocity, initial velocity, okay? So here is your position as a function of time. And you see it's a quadratic function, so that means the acceleration will be constant, okay? So this is giving you your position as a function of time. And here's again position. When the acceleration is constant, your average velocity can be calculated like this. Final velocity plus initial velocity divided by 2 times time. Okay. Your velocity as a function of time. Velocity is a linear function of time. Okay. And here's another formula. What this gives you is your final velocity square is equal to your initial velocity square plus 2a times the displacement. So here's a formula that's giving you your velocity as a function of your location, as a function of your position. I'm sorry? In just a couple of periods, you'll be an expert at this. Again, it's not hard. Okay? Trust me. Okay, so this is showing you the derivation of that. We won't go through this. Again, velocity is a function of time. And when is this valid? Only when acceleration is constant. If the acceleration was changing with time, you couldn't use this formula. Okay? So this is velocity as a function of time. Velocity is linearly increasing with time. Here's position as a function of time. Okay, it's a quadratic function of time. And that's when acceleration is constant. Okay, this is deriving that, but we won't worry about that. Okay, so here's one motion that you see that has a constant acceleration. Freely falling objects. Okay, so here's a freely falling object. Okay, what this means is the only force on this guy is the force of gravity. Okay. Right, so this is a freely falling object. What that? A freely falling object. No, you're right. Why? Why not?
Resistance.
Very good, my friend.
Very good.
You see, in this case, the air resistance was negligible, as our friend said. Here, a freely falling object just means an object on which only gravity acts. And in this case, there was air resistance, but that was negligible compared to gravity. In this case, air resistance was not negligible. Okay? The acceleration of this guy was 9.8 meters per second squared in this direction. Here, there were multiple forces that were relevant, and so the acceleration was not 9.8. So that's what we mean by freely falling objects. And that's the only example, that's one of the few examples we have where the acceleration is constant. Okay. All right, so acceleration is a vector, and it's pointing downwards, and we give it a special name, and its magnitude is 9.8 meters per second squared. Okay? All right, fellas, you guys